Final lesson, we are going to be looking at how light waves and refraction are exploited in order to produce different types of images, such as magnified images, images on a projector screen, so on and so forth. Unfortunately, not holograms. Um, so that's going to form the basis for last lesson of this unit, 7.5 optics. So here's some starting terms and concepts that we'll need, at least prior to our lab that we did in class. Unfortunately, as you guys know by now, this video will not contain a lab. So some starting terms: light rays diverge. All right, so if two light rays are if a series of light rays are diverging, that means they're moving away from a central point and getting farther away from each other. Okay, converge on the hand means that light rays are going to move towards a central point and intersect. A virtual image is an image that cannot be projected onto a screen. The image forms behind the lens on the same side as the object. This may not make very much sense right now and seem very abstract. I'll give you some examples on the next slide, and then we're going to provide a more formal definition of virtual images downline in this class. And accompanying virtual images are real images. So real images are images that can be projected onto a screen. The image forms in front of the lens on the other side of the camera. So real versus virtual. So an example of a real image would be, say, like a movie theater screen. You have this projector at the back of the movie theater. The projector shines light onto film. The film is the object that we want to see. And the light passing through the film passes through a lens and projects the image onto a screen. So the image is forming on the other side of the projector opposite where the film roll is at. Whereas a magnified image, or excuse me, a virtual image, the image forms on the same side of our object that we're looking at. So if we look at right here, this is an example of a virtual image. We have this lens right here, or we have this ruler right here that we're magnifying, and we can see that the image that we see of the magnified ruler is on the same side as the ruler itself. We have to look through the seeing glass to see the image. So our virtual image forms on the same side as the object we're looking at, whereas with a real image, the image forms on the opposite side of the object that we are interested in looking at and seeing. In addition, for our image formation inquiry lab, our students had to know a little bit about concave and convex lenses. So a concave lens is a lens that bends inward at the middle, and a convex lens bulges outwards at the middle. And this line that bisects the middle of both lenses is what we call the principal axis. It's kind of like our starting point for the lenses, okay? So here's a quick check for prior knowledge. In two or more sentences, describe to the best of your ability how a magnifying glass works. Use diagrams as you feel is necessary. Alright, so now we're moving on to 7.5 optics. Some announcements here. Let's not worry about announcements since this is just a video lesson. So here's what we're up to today. Discussion of lab results. We won't cover that since that requires participants being in class. So we'll just jump straight into image formation theory. We'll go into how do lenses work based on refraction and the properties of light waves. We'll look at magnification, okay? What is magnification and what causes magnification? And then we'll look at how to predict what type of image forms for a given set of circumstances using a nice little tool known as a light ray diagram. So we'll look at light ray diagrams for convex lenses, concave lenses, mirrors, and refraction between surfaces, and we'll look at the major types of images that can form in both cases. Or in all cases, excuse me. Alright, so discussing our lab results, we'll skip over right here. So how do lenses work? The general theory, okay? So light rays are refracted by the lens, okay? So our lens exploits refraction to bend our light waves, bend our light rays, better said, since we're looking at it from the perspective of a light ray instead of a light wave in this lesson. So lenses are designed to refract light so the light rays intersect. For a convex lens, that is. For a concave lens, something else slightly different occurs. We don't get refraction, we don't get light rays intersecting, we get virtual light rays intersecting. The focal point represents where light rays a very far distance away intersect at, okay? So if we have an object that's really far away, so like the sun, or say like mountains off in the distance, light rays from those objects are going to be basically parallel to each other, and when they pass through the convex lens, they're going to be bent through what's known as the focal point. So the focal point is where all these light rays a very far distance away are going to intersect at. A focal point exists on both sides of the lens, since we can equally pass light from this side through our lens and have our light intersect on the other side of the lens. All right, so the focal point, or better said, the focal length, combined with the object distance, which we'll take a look at in a second, influences where our image forms, aka the image distance, and that allows us to determine how to change the settings of our camera in order to determine a sharp image. But we'll take a look at that down the line. For right now, let's jump to a quick think, pair, share. From the perspective of light waves and the focal points of a lens, how is a magnifying glass able to set objects on fire under the right conditions? Why is it that magnifying glass can set, say, something like kindling or tinder on fire under a specific right condition, and what is this specific right condition? Take a moment to pause the video, answer this question, and then we will resume shortly. All right, so let's take a look here. So what is happening? So the light rays from the sun, all right, are basically parallel to each other because the sun is so far away. So as a result, as they pass through the convex lens, they're going to converge and be refracted through the focal point, okay? So as a result, we have basically the whole intensity of all the light from the sun concentrated on a single point. Remember that light waves carry energy in the form of thermal radiation. So as a result, you have a concentrated, highly concentrated amount of thermal radiation on this point right here, which is what is going to cause the paper to ignite and burn. And the specific condition that we need is that our object has to be placed right at the focal point of our convex lens. Okay, if we have our object placed a little bit closer, say right here, our light rays are going to be dispersed, and there's not going to be any convergence. So as a result, our paper will ignite. Whereas if our paper is a little bit too far away, the light rays are going to start to spread out again once they pass this focal point, and that's going to result in a dispersion of light waves on our paper again, and thus our paper is not going to ignite. So image formation theory, okay? So we're not going to go through the whole geometry of this, nor are we going to bring up the infamous equation used to predict where an image will form. But basically, image distance, where an image forms at, the image distance is influenced by two factors, the object distance and the focal point. So the image distance, so the object distance is the distance from the object to the center of the lens, like we see right here. Whereas the image distance is the distance from the center of the lens to where all light rays intersect. Where our light rays intersect at is where the image is going to form. Okay? So object distance and focal point thus influence where our light rays intersect and thus influence our image distance. We're not going to go into, again, the whole geometry of it, but if you adjust the object and you adjust the focal length of your lens, let's say you switch out a different lens, then that's subsequently going to affect how your light rays are bent, and that will affect your image distance. This will be seen more commonly when we get to, this will be seen much more easily when we get to light ray diagrams. So again, I'm not going to throw any equations at y'all or anything like that with this. So a sharp image forms when a screen, i.e. like a film, a camera film, or a movie theater projector screen, is placed at the image distance, resulting in a sharp image. All our light rays converge right on the film or right on the digital chip of our digital camera or whatever we're using. And then blurry images occur when our image distance is not aligned with the screen or digital chip of our digital camera. So as a result, the light rays are dispersed from the light rays coming from our object are dispersed, and that's going to give us a blurry image since we don't have our light rays concentrated on a single point. So in order to have a sharp image, we need this image screen, we'll call it for the time being, to be perfectly aligned with our image distance. Essentially, as we'll see in a second, when you adjust a camera lens, you're essentially adjusting the image, you're essentially moving your lens to adjust the object and image distance in order to have the light rays converge on your screen. Since what happens with a camera is the screen can't move, we can't adjust the screen to align with our image distance, so we have to do the reverse. We have to adjust our object distance so that the image distance adjusts to align with our screen. All right, so we have to adjust object distance in a digital camera, hence why you twist the lens and adjust the length of the camera lens. So that way, the object distance influences the image distance to the point that the image distance lines up with the screen. So here again is an example right here. If we have this film right here that's not lined up perfectly, we're going to get blurry film. Except in most digital cameras, as I've already talked about, the film is fixed or the digital chip is fixed in place. So instead of the film moving around, the lens moves around until the image distance lines up with the fixed screen. And so that's why you can twist a camera lens in order to adjust the camera lens position. And then here's just another brief example. We can adjust our camera lens in order to adjust the image distance. And so what this results in is that, say, at certain times, if we adjust the lens in one way, light rays that are from the foreground of an image will converge on the screen of our camera, resulting in a sharp foreground image, while the background light rays are not going to converge on our image screen, resulting in a blurry background. And then vice versa, you can adjust the lens until the opposite effect happens, where the foreground is blurry and now the background is sharp. So convex versus concave lens, let's jump back into this, go into a little bit more detail. So a convex lens refracts light inwards. The light rays converge to form a real image, okay? So if the object is inside the focal point, a virtual image will form. So that is a big thing to note, all right, is that if our object is outside of the focal point of a convex lens, a real image will form, whereas if your object is inside a focal point, a virtual image will form. All right, if you're a little bit confused about that, just take it at face value. We're going to start from face value and dig deeper from here, okay? The difference between a concave lens is a concave lens will refract light outwards, like we see right here, and like was explored in our lab. Thus, the light rays will diverge. In order to see what our image looks like, we have to trace our light rays backwards behind the lens to form a virtual image. So what distinguishes a real versus a virtual image? So a real image forms as a result of light rays converging. All right, so again, that's why with a convex lens, we noted in our lab that a real image formed with convex lenses because we have real light rays converging and our image formed on the opposite side of the object we were looking at, just as I had mentioned earlier. Whereas with a virtual image, the virtual image forms as a result of light rays diverging. There's hypothetical virtual light rays that we trace backwards and intersect, and this gives the resulting image that we see. If you're wondering why we can see an image if these are virtual/hypothetical light rays, the reason being is that the light we see the light on the path as it approaches us. Better said, when the light hits our eye, we're going to see the light traveling on this path right here. So our eye perceives the light to be moving on this path right here, and hence we're going to see the light rays dictated by hypothetical or image formed by these hypothetical light rays. So yes, these light rays don't exist, but is the path that our eyes perceived based on how the light enters our eye, which is at this diverging paths right here. So as a result, that based on the path that the light enters our eyes, we trace our eyes perceive that light going backwards as intersecting back here. So it's a little bit of illusion, kind of, sort of, in a way. But as we'll see, not really so much, because it does actually result in image formation, actually does play a role later on when we get down to modern physics in a phenomenon known as gravitational lensing, specifically the formation of a phenomenon known as Einstein rings. So now we're going to look at how images form for different types of lenses. So F right here represents our focal length, okay? And then we have our principal axis, we have our object, we have our image, okay? So convex lenses. So when placed outside the focal point, the rays have refracted inward on a convex lens and thus intersect on the other side of the principal axis, so the image will be flipped. Here's a procedure that you will need to follow for any and all lenses to see what type of image will form, okay? The first thing you're going to do is draw a parallel light ray from the top of the object, okay, like this right here. It's going to be parallel to your principal axis. When it passes through a convex lens, it's going to get bent through the focal point. So your first light ray that you're going to draw is going to run parallel to principal axis and then get bent through the focal point, okay? That is the first step you need to do. The second step is draw a second ray that runs through the middle of the lens. No refraction will occur. It's just going to go straight through, and it's going to intersect with the first light ray. So the point where the two light rays intersect at is going to represent where your image forms at. These two rules are going to be the bedrock for all other light ray diagrams that we do in this lesson, okay? So let's move on then to the one example where we have a convex lens resulting in a virtual image. Okay, well before that, actually, forgot about this, we have the human eye. So the human eye is the example of a convex lens. It bulges outward. So what's interesting about the convex lens of the human eye is that the human eye actually causes the image to form upside down on the back of our eyes, but our brain recognizes this, the optic nerve and brain communicate to recognize this, and the brain actually turns the image right way up as it should be. So that's actually pretty interesting. So now we're going to look at magnification. How do convex lenses result in magnified images? Okay, so convex lenses, if you place an object inside of a focal point of a convex lens, the light rays are going to refract inward the same way as they do on our prior slide, except now the light rays are going to diverge as they move towards the eye. So the rays are going to be traced backwards to form a magnified virtual image. So here's our procedure to follow, okay, in order to determine what this magnified image will look like. It's the exact same procedure as before, except with one additional caveat. So we're going to start off again by drawing a parallel light ray that gets bent through the focal point on the other side of our lens. And then we're going to draw a second light ray that goes straight through the middle of our convex lens, all right, and is not bent at all. We can see right here these two light rays are going to diverge, so they're not going to intersect. So what do we need to do? Well, we're going to trace the light rays backwards, okay? And the light rays are going to intersect, these hypothetical light rays are going to intersect behind our object, and that's going to result in this magnified, blown up image that we see right here. So magnification is nothing more than the result of the geometry of light waves and basically how convex lenses work with diverging, converging rays. So again, what's going to happen here is our eyes perceive these diverging light waves, diverging light rays to be moving on this path right here. So we see the light ray, this light ray moving on this path right here, and we trace that backward. Our eye traces that backwards in order to see the path that this light follows, hypothetically speaking, if it were to be traced backwards. And then this light ray, our eye traces back through this path right here, and so the resulting intersection, based on what our eye perceives, is what results in the magnified image. So next we're going to move on to concave lenses. Concave lenses cause a phenomenon that's known as demagnification, where our image is actually smaller than our object. Okay, so with a concave lens, light rays will always be diverged, and a demagnified virtual image will form. You can actually get magnified images with concave lenses, but we're going to keep things simple for right now and focus strictly on the demagnification, since that is the primary purpose and interest of a concave lens. So the process to follow is the same as before. So we start off with our object and we draw a parallel light ray. All right, except this light ray with a concave lens is going to get bent outwards now instead of bent inward. Now we draw a second light ray that passes through the center of our concave lens, just as we would expect. So we're following the same rules we established before. And now because these are diverging light rays, we have to trace backwards in order to see what image will form. In this case, the only light ray we have to trace backwards is this light ray right here. So we see that our light rays are going to intersect right here, resulting in this smaller upright virtual image. Again, it's virtual because one of our light rays is virtual. It's a hypothetical light ray. And also because the intersection occurs on the same side as our object. So again, I cannot reiterate enough, this is the bedrock right here. One parallel ray right here that either bends outward for concave or bends inward for convex. All right, a second light ray that runs straight through the middle of the lens and is unaffected. And then we look for point of intersection. If we have to trace backwards, we do as such. Note right here also that this hypothetical light ray right here, okay, also passes through the focal point on the same side of our object. So the light ray that is parallel, when it gets bent through, is either going to bend through the focal point if it's a convex lens, or it's going to bend through the focal point on the same side as your object if it's a concave lens. Okay? So magnification in a nutshell, convex lenses causes magnification when object is placed between the focal point and the lens. And concave lenses will always create virtual images that undergo demagnification. Again, there are conditions when concave lenses can cause magnification, but we are going to ignore those conditions for right now. So now we're going to come to our last two types of images, which are going to be reflected images and refracted images. So we're going to look at how mirrors work right here. So a mirror results in a virtual image. All right.
However, the weird thing about mirror is that the virtual image forms on the other side of the object as opposed to the same side of the object. So why is it a virtual image? Well, the reason being is we can't project a mirror image onto a screen. Um, and in addition, a mirror image forms from virtual light rays. So how does this form right here? So what we're going to do right here, our procedure for mirrors, is we're going to draw two light rays as we've done so far, and both these light rays are going to be diverging, getting farther and farther apart. All right. So now these light rays are going to reflect off our mirror and continue to diverge. So since our light rays are diverging, they're not going to intersect on this side. So we need to trace them backward based on the paths that our eye would see the light rays traveling on in order to find a point of intersection. So our eyes would see the light rays traveling on this path right here. And so that leads us to trace our light rays backwards to get this point of intersection, which results in the virtual image that we see. So pretty cool. And then lastly, we come to refracted images. How is it that a pencil, if you place it in water, looks like it'll be bent or misaligned? So this results, again, from refraction. That's basically been the whole topic of this lesson has been refraction applied to how images form. So with a refraction, a virtual image is formed because the image is on the same side of the object, and not only because of that, but also because your light rays are going to be virtual. The intersection light rays are going to be virtual here. So here's your procedure to follow. It's kind of similar to mirrors, except slightly different, okay? So you're going to draw two light rays diverging from your object, just as we did with a mirror, until they reach the medium barrier, all right, the barrier of the two media. At the barrier, the light rays are going to bend and continue to diverge as they go towards the human eye, okay? So we're going to connect the diverging light rays to the human eye. The light rays are going to get farther apart. Because our light rays diverge, that means they're not going to intersect on this side right here. So we're going to have to trace them backwards based on the paths that our eye would perceive in order to find the point of intersection and thus what our image will look like. So we trace the light rays backwards in the diverging medium until they intersect in the original medium, and that's where they intersect at is going to give us our original image, resulting in this bent, kinked pencil that we see right here, just as we see actually happen with objects when we place them in water in actual everyday life. And this is our lesson on image formation and optics.